Hello everybody. We are going to be dealing with trigonometric identities. Now, there are like two identities that we really need to know with grade 11 right now, and then grade 12 you'll learn like a couple others. But for now, let's stick to these two. They're very basic, and we're going to learn how to apply them in certain types of questions. So you're going to see in the examples, I'm going to do 3 different types of questions, and you'll see right after we've dealt with the identities. But I'm not just going to show you the identities, I'm actually going to just prove them, right? Just to make it a little bit understandable on why they are the identities they are, right? Why they are the way they are. That's what I was trying to say. So the first identity that we're looking at, right? And I'm going to prove both of them, okay? The first identity is going to be sine squared theta, okay? So sine squared theta plus cos squared theta is equal to 1, okay? So that's the first identity we're going to be dealing with. And the second identity is going to be tan theta is just going to be equal to sine theta divided by cos theta, okay? So those are the two identities we're going to be having a look at. And the only way that we can prove them, well actually I would say the best way to prove it is by using the Cartesian ratios for trigonometry, okay? It's a lot of words coming out of my mouth there, and that's why it's almost like a tongue twister. So let's get into the first proof, okay? So proof number 1, okay? So number 1, the proof, okay? Notice that we have sine square theta plus cos square theta is equal to, we don't know what it is equal to, right? We see it over here, but let's just assume we don't know what it is, okay? So let's do that. What else can this be written as? If you saw the last video or the grade 10 revision, we know that we can rewrite this as sine theta squared plus cos theta squared, okay? Such that we can now use the Cartesian trig ratios to now go further with the question. Remember that sine theta is equal to y over r, okay? Sine theta is equal to y over r, and we square that, and cos theta is just equal to x over r, okay? And we square that. From here, we use our properties that tell us that x divided by y squared is the same as x squared over y squared, where the square will distribute between the denominator and the numerator. Meaning, if we look at y over r all squared, it'll be y squared divided by r squared. Plus, if we look at x over r squared, it's going to be x squared over r squared. And notice that the denominators are common, right? Meaning we can rewrite this two fractions as 1, right? The LCD method. Meaning we're going to have y squared plus x squared divided by r squared, okay? For this one. Now, where would we go from here? Now, notice that y squared plus x squared is actually very similar to an equation that we know from Pythagoras, or a circle equation, right? X squared plus y squared is equal to r squared. That is the equation of a circle, or in your case when you're learning, this was the Pythagorean theorem, okay? And notice that y squared plus x squared is actually the exact same as this. Meaning, y squared plus x squared, or x squared plus y squared because they're commutative, is equal to r squared. So we replace it with r squared. So it's r squared divided by r squared, which is 1. So this is the proof on why sine squared theta plus cos squared theta is actually just equal to 1. So it'll always work like that. And notice that you need to be careful, right? You see theta, right? These theta values must be the same. So I'm going to state here, this thetas, these two must be equal, okay? The theta values, in order for this identity to work. So if you have sine squared 30 plus cos squared 60, for example, that will not actually satisfy this identity because the angles are different. So just be careful of that. So that is the proof of the first identity. Now let's do the proof of the second identity. Then we go straight into the applications of these identities, which are just the questions that they'll ask in the examinations or just your homework or wherever you're going to be in life. So the second identity that we actually have is tan theta is equal to sine theta over cos theta. Now, when we're proving this, we can't just use the left side because it's helpless. But however, we can use the right-hand side, right? We kind of need to prove here that the right-hand side is equal to the left-hand side. I know you guys don't like the proof questions. It's a lot. But this one, however, is a very lenient one. So let's deal with this proof, right? We're going to do the right-hand side, okay? So what you would indicate is you would say right-hand side for the proof, obviously. And remember what we have, okay? We have sine theta over cos theta. And remember that sine theta, okay, is in Cartesian plane form. It is y divided by r, okay? And this is all over cos theta, which is x over r, okay? And we need to simplify this. You notice that there's a fraction divided by a fraction, so we want to use tip and times method, okay? That's a method that I usually use, where you can rewrite it as, we know it can be rewritten as y divided by r divided by x over r, right? We can rewrite it like this. And if we tip and times, all we are going to do is we're going to say y over r multiplied by the reciprocal, the flipped over version of this fraction, which is r over x. And if we use multiplication of fractions, we can multiply the numerator with the numerator, and then we can multiply the denominator with the denominator, such that we have y times r divided by r times x. Okay, and notice that the r's can cancel. And then we're left with y over x. And this is the best part. We know, according to the Cartesian trig ratios, that tan theta is equal to y over x, which, remember, y is the opposite and x is the adjacent. Tan is opposite over adjacent. So therefore we just proven that sine theta over cos theta is indeed just equal to, equal to tan theta. Okay. And then obviously at the end you can say, therefore, left-hand side equals right-hand side. So you can say, therefore I'm smart. Therefore I've proven everything over here. Okay. So this one is a very basic one. Now let's get into actual applications of these identities, where the real stuff actually happens. So here's our first example. We need to express sine theta over tan theta as a single trig ratio, right? So the first type of question that you could get is to express some expression, right, as a single trig ratio, meaning we need to rewrite it into a way that we have either maybe sine, cos, or tan on its own, right? Or maybe a reciprocal of that. Sometimes they'll give a reciprocal, but usually you want one trig function on its own, right? So we're going to try and simplify it in that sense. So it's usually just simplification using identities, okay? So first things first, we are starting off with sine theta divided by tan theta, right? And notice that our first identity that we know about is the tan theta identity, which is equal to sine theta over cos theta, right? That's what we can really do. There's nothing else that we can really do from here. So usually you would want to actually run through your options. I know when you're in an examination, you're like, oh shoot, but which one should I do exactly? I would say, try and look at all your identities that you know, and use them one by one to see which one simplifies them. when we get into the proof question, sometimes it's like you need to know factorization or difference of two squares or rationalization. But however, if you get to a point like this, you can really only rely on your identities. Okay, so we know that this can be rewritten as sine theta over sine theta over cos theta. Okay, because that is the identity of tan theta. Okay, and we can use tip and times, right? So this would just be sine theta divided by 1 divided by sine theta over cos theta, right? If we were to rewrite it in division form. And then if we tip and times, we are going to have the same sine theta over 1, but multiplied by the reciprocal, which is just going to be cos theta divided by sine theta. Okay. And notice, if we were to multiply the fractions in, the sine thetas will cancel out. And then we just left with cos theta over 1, which is just the same as cos theta. Okay. So therefore, sine theta over cos theta, tan theta, okay, this is just going to be equal to tan theta. And this is what the single trig ratio is, because obviously this is a trig ratio, which is cos theta. Okay, so that's how you answer this type of question. So this is the type of question that you'll get, and usually these are the more like simpler type of questions. Let's get into the next type of question though. So here's another type of question, right? Example 2 says, determine the value of sine theta plus cos theta all under a square minus 2 sine theta times cos theta, okay? So the value, meaning an actual like finite value, okay? We need to find a way to simplify it such that we actually get a value so we can answer the question. So what can we do with this question? Well, we can't really do much from here other than maybe expanding this bracket, because notice that it's under a square, meaning we can expand it, okay? So I'm going to rewrite the thing over here. So sine theta plus cos theta all squared minus 2 sine theta cos theta, okay? And this is just going to be equal to, if we expand the brackets, notice that we're going to get the following. And I'm going to actually write it on top here, okay? So sine theta plus cos theta multiplied by sine theta plus cos theta. Okay, so we need to use the FOIL method. Okay, so it's the first, we multiply the first two, okay? So it's going to be sine times sine, which is sine square theta, right? And then the next one that we have is the outer, which means we're going to multiply the outer values, which is sine and cos. So we're going to say plus sine theta times cos theta. And then the next one is the inner, which is going to be cos theta times sine theta, which is just, let's just say sine theta times cos theta, because they're both the same. And then the outer, the last, which we are going to be cos theta times cos theta, which is just going to be plus cos squared theta, okay? And then we obviously have minus 2 sine theta cos theta, okay? Now, if we were to look at it this way, we have sine theta cos theta plus sine theta cos theta, which is just going to be, so we're going to have sine squared theta plus 2 sine theta cos theta, because notice that this and this are actually like terms, and their coefficients are 1. So it's basically 1 plus 1, which is equal to 2. And obviously this is just our variable. You can actually rewrite this as x if you want to. So it'll be x plus x, which is going to be 2x. Okay. And then we have plus cos square theta minus 2 sine theta cos theta. Okay. Notice that we can cancel out this 2 sine theta cos theta with the negative 2 sine theta cos theta. Therefore, we just left with sine squared theta plus cos squared theta. Doesn't this look familiar? This is our identity. sine squared theta plus cos squared theta is just equal to 1. That is our identity that we have, okay? So that is going to be the answer to this type of question where you have to determine the value. So the value of this expression over here is just simply 1. So here's the other type of question they can ask. This is example number 3, and it says prove that tan squared theta minus sine squared theta is equal to tan squared theta times sine squared theta. Now I know these types of questions are very challenging. They will ask very intense questions, especially for examination settings. However, there's actually a very easy sequence to all of this, okay? It doesn't really make it like super easy, or it actually makes it much easier, I'm not gonna lie. Notice that we need to work on like maybe one side, and then we also got to see if this side is equal to the other side, right? But we want to use the one side where we're able to apply identities that we know, and that makes it much easier. And in this case, if we think about this, right, tan squared theta multiplied by sine squared theta is just going to give us, right, we know tan theta is equal to sine theta over cos theta, right? And if we take tan squared theta, it's going to be sine squared theta over cos squared theta, because the square is going to affect both of them, right? But then we're going to get to a point where we have sine to the power of 4, which makes this one weird, and it's not going to be like easy to deal with, right? So it would be much easier to deal with the left-hand side, because now what we can do with the left-hand side is we can rewrite it as follows. I'll show you right now. So the left-hand side, we can do this, right? We know here that tan squared theta minus sine squared theta, this is the same as sine squared theta over cos squared theta, okay, minus sine squared theta, okay? And then from here, we can just rationalize, right? Because usually we want, in this case, we want it to be in one expression, right? We can see there's two terms, and this is one term. So we want to actually put it into one term, okay? And see what happens. So let's rationalize this, okay? So in order for us to rationalize this, we need an LCD, a lowest common denominator. We need common denominators. Notice we have a denominator of cos squared theta, meaning we need this term to also have cos squared theta. And in order for us to do that, we need to rationalize the second term. And this is how we do it, okay? We're going to minus it by sine squared theta, but we're also going to multiply it by the denominator here, cos squared theta, and then divide it by that same exact expression, okay? Such that it still stays true, and this is actually the exact same as this, because when you cancel these out, you're just left with sine squared theta. But remember, we want to rationalize it, meaning we want similar denominators so that we can rewrite it into one fraction. Okay, so because we have the same denominators, we can now say that the numerator here, sine squared theta, is going to subtract with this numerator, sine squared theta, multiplied by cos squared theta, and this is all divided by cos squared theta, okay? And then from here, what do you notice? We have a common factor of sine squared theta, okay? Sine squared theta is a common factor, so we can actually take that out. Sine squared theta, and then we're left with 1 minus cos squared theta, okay? Because notice when we take the sine squared theta out, we're just left with 1, because we're basically dividing it by sine squared theta, which gives us 1. And then we divide this one by sine squared theta, such that what we get is just cos squared theta on its own now, okay, because we took it out. And this is divided by cos squared theta, okay. Now from here is an identity. Now you're probably wondering, what? What are you talking about the identity? This is not an identity. Now, here's the thing, right? We kind of need to know the manipulation of our identities as well, but mainly only one of them for this instance, okay? So we can look at it in this instance over here as the identity that says sine squared theta plus cos squared theta is equal to 1, right? However, there's two ways we can also rewrite this, where we express it as sine squared theta and take cos squared theta on the other side, such that we have 1 minus cos squared theta, and the other version where we can take sine squared theta over, where we have cos squared theta is equal to 1 minus sine squared theta. Okay? These are the two variations of this identity. So when you see these patterns, you would already know this goes into one term. So you reduce it from two terms to one term. And that's usually what this identity can also do. That's the best part about this identity right now. Okay. So basically what we notice is that we have 1 minus cos squared theta, which is actually equal to sine squared theta. Okay. So therefore, we're going to have sine squared theta times sine squared theta divided by cos squared theta. And notice that we want to prove that is equal to tan squared theta times sine squared theta. We have sine squared theta, and we see here that we have sine squared theta over cos squared theta. Can you see that over here? We have this. Okay. And this whole thing is just tan squared theta. Therefore, this is just going to be equal to sine squared theta times tan squared theta, which is equal to the right hand side. Okay, this part is equal to this part over here. And now we've just proved this one. I know these types of questions are usually the more intense ones, so that's why I want to do one more example. So here's the last question I'm going to do for this video. Prove that 1 minus cos theta over sine theta is equal to sine theta over 1 plus cos theta. Now here's a problem. We can't use any factorization for this one, and we can't really simplify using identities right now. So when you get this in an examination, you might panic, but however, remember these identities that we just went over, or I guess the same identity but manipulated? Do you notice that we have a 1 minus cos theta here, right? We have a 1 minus cos theta right over here. And we also have a 1 plus cos theta, but however, let's focus on the 1 minus cos theta. We really want it to be 1 minus cos squared theta, so we can rewrite it as sine squared theta, right? Using our manipulated identity. There is a way to do this, by the way. And this is what you call using a conjugate. I'll explain right now, okay? We need to rationalize the left-hand side. So it's actually easier to use the left-hand side right now. So the left-hand side, we have 1 minus cos theta over sine theta, okay? We want this to be in the form of 1 minus cos squared theta. But in order to do that, we need to rewrite it in the form of difference of two squares. Because remember, 1 minus cos squared theta, 1 is a square, a perfect square, and cos squared theta is also a perfect square because it is squared. Okay. So therefore, this is what we can do, right? We can say 1 minus cos theta, okay, divided by sine theta, but we can multiply by the conjugate meaning the exact same expression with the changed sign, okay? So we're going to multiply it by 1 plus cos theta over, and then obviously we have to write 1 plus cos theta, because remember, this is the same as 1, okay? We're multiplying by 1. This is allowed, but we want to manipulate it so that we can change things around, okay? This is what you call the conjugate method, where you can rationalize something in terms of something else. And we got it now in the form of, do you remember perfect squares? A minus b multiplied by a plus b. Do you notice that form over here? Which is then going to be equal to a square minus b squared. Okay. So that means what we can do is in the numerator, we have a minus b times a plus b, which is equal to a squared minus b squared, where a is equal to 1. So 1 squared, which is a squared, is going to be 1 minus b squared, which is cos theta squared, which is cos square theta, okay? This is divided by, also notice we reduced it to this form now, okay? Now we can deal with the denominator, which is sine theta multiplied by 1 plus cos theta. Remember, we still have that. So sine theta multiplied by 1 plus cos theta. Okay. Now we can replace this with our identity. We know that 1 minus cos squared theta using the identity is just sine squared theta. Okay. Over sine theta 1 plus cos theta. Okay. And notice that we can cancel out the sine squared theta with one of the sines on the bottom. Therefore, we're left with sine theta on its own, all divided by 1 plus cos theta. Okay. And notice this is exactly the same as this. Sine theta over 1 plus cos theta. So that is why you need to try and force your way to get your identities. So if you can't actually find the identities, usually you need to manipulate it such that you could get the identities, if you understand what I'm saying here. So therefore this is going to be equal to the right hand side. Okay, so left hand side is indeed equal to the right hand side. Here's the last example that I actually want you guys to try on your own. It says prove that 1 plus 2 sine theta cos theta over 1 minus 2 sine squared theta, remember there's a 2 here, is equal to 1 plus tan theta over 1 minus tan theta. Now these are the types of examples where you may have to manipulate both sides. But usually you would want to try and manipulate the one side until you can't really manipulate it anymore, and then you'll have to swap to the other side to try and manipulate it to whatever you found on the left hand side. So this is that is the hint that I'm going to give to you for this one. So I would recommend using that advice to be able to answer this question.